Okay, let's try problem 7. For how many ordered pairs of positive integers a comma b with 1 less than or equal to a and b less than or equal to 64 are a over b and a plus 1 over b plus 1 both odd integers? So we obviously don't want to just run through every single ordered pair, right? Because that's just way too much work. So we need to think of a better approach. The next thing we want to do is actually find which ordered pairs a comma b satisfy this property. So for simplicity, we call such an ordered pair spicy. So we want to find which ordered pairs are spicy. So if a comma b is spicy, that means a over b and a plus 1 over b plus 1 are both odd integers. And in fact, since a and b are both positive, we actually know that these are odd positive integers. Okay, but how can we use this condition, combine these two conditions to form one? If we subtract 1 from both of these fractions, we get a over b minus 1 and a plus 1 over b plus 1 all minus 1. And these are now even non-negative. Integers. So a over b minus 1 simplifies to a minus b all over b, and the expression on the right simplifies to a minus b over b plus 1. So these are both even non-negative integers as well, because they're just the same as before. So what does this tell us? We know that a minus b over 2b and a minus b over 2b plus 1 therefore must be non-negative integers, right? So since we can easily calculate LCM of b and b plus 1, 2b and 2b plus 1 to be 2 times b plus 1, then we actually know that since 2b divides a minus b and 2 times b plus 1 divides a minus b, then 2 times b plus 1 also divides a minus b. So that means that a minus b is of form 2 times k times b plus 1 for some positive integer k. Sorry, non-negative integer k. So we were at k is greater than or equal to 0. So now I think we can kind of start to count how many how many such pairs there are. So a equals 2kb squared plus 2k plus 1b, I think. Yeah. Okay, now comes the really messy part. When k equals 0, how many solutions are there? Well, all such pairs are of form a comma b, right? And 1 is less than or equal to a and b is less than or equal to 64. So we have 64 solutions right off the bat. What if k equals 1? Now, in this case, pairs are of form 2b squared plus 3b comma b. And we know that 2b squared plus 3b is always greater than or equal to b when b is in this range. So when 1 is less than or equal to 2b squared plus 3b is less than or equal to 64. So we count how many values of b satisfy this. We know that b is greater than or equal to 1, right? And if we kind of calculate it, like we just we could just run through values. So let's say b equals 2. 2b squared plus 3b equals 8 plus 6 equals 14, which is still way too small. Let's go higher. Let's try b equals 5. 2b squared plus 3b is 50 plus 15, which is 65. Oh no, that's way too high. So we try b equals 4. 2b squared plus 3b equals 32 plus 12, which is less than 64. So we know that for k equals 1, we have 4 solutions because we can plug in b equals 1, 2, 3, or 4. Let me erase this stuff. So what if k equals 2? If we plug it into this formula right here, we have that the possible pairs are of form 4b squared plus 5b, comma b. So that means 1 is less than or equal to 4b squared plus 5b is less than or equal to 64. Again, b equals 1 clearly works. So we try to find the upper bound like before. So b equals 4 worked for k equals 1, so that's a good upper bound to try for this one. If b equals 4, we get 4b squared plus 5b. We can calculate that it's 64 plus 20, which is too big. So let's try b equals 3 now, because this function grows super rapidly. 4b squared plus 5b is 36 plus 15, which is small enough. So for k equals 2, we have 3 solutions for b equals 1, 2, and 3. Now what about k equals 3? We get 6b squared plus 7b comma b. And again, we try the upper bound of b equals 3. So we get 6 times 3 squared plus 7 times 3, which is 54 plus 21, which is too big. But b equals 2 probably works. 6 times 2 squared plus 7 times 2, which is 24 plus 14, which is small enough. So k equals 3 has 2 solutions. Now, we could keep on doing k equals 4 and k equals 5, but at this point we realize that there's probably going to be a lot of values where b equals 1 and 2 work. So what's the largest value of k where b equals 2 works? So we have a equals 2k times 2 squared plus 2k plus 1 times 2, which is equal to 8k plus 4k plus 2 equals 12k plus 2. Yeah, this seems right. So when is this less than or equal to 64? This is less than or equal to 64 when k is less than or equal to 5. So k equals 4 and k equals 5 provide 2 more values. So now for all remaining values of k, it either provides one solution or no solutions. So for what k do we have one solution? Let's just get rid of this first. All right. So equivalently, we want to ask, when does 2k times 1 squared plus 2k plus 1 all times 1, when is that less than or equal to 64? Well, this is equal to 2k plus 1 is 4k plus 1, which is less than or equal to 64 when k is less than or equal to 15. So for the values k equals, when k is in the range 6 to 15, we get one solution. Okay, therefore, the total number of solutions is 64 plus 4 plus 3 plus 2 times 3 plus 1 times 10. So 64 plus 4 plus 3 plus 2 times 3 plus 4 times 10. And we can calculate that this equals, oh wait, did I say 4 times 10? I meant 1 times 10. So we can calculate that this equals 87, which is our final answer.